So I'm Ludmilla. I am the data and code curator at iDiv. Before that, I did my PhD I studied biology and I did my PhD in biology as well. So studying ecological modeling. And it's because of my experience around that time with managing my own work and managing code and publication of getting people's data and so on that I got involved into research data management. And then I got this job at iDiv, where I basically get to do it constantly. So the bulk of my work is reviewing people's data before they want to publish it in the iDiv data portal. But we also offer the code revision. This is less sought after. I'm not sure why. People are shy, I think, sometimes. So today I'm here to show you how you can publish your workflow. And the publishing itself would be very simple step. It's like relatively straightforward, but I'm here to show you how you can make it part of your workflow, of scientific workflow, without it being too much of a added work for you to take care from now on. So just a quick reminder, right? Why we want to publish our code. I'm basing myself on this publication by, let me just get the pointer. This publication from Marwick and Buttingen and Mullen, where they define the dimensions of reproducibility as the empirical part, the statistical part, and the computational part. Now, the empirical being the reagents that you use, the cells, the instrument setting, the experimental setting where you collect your data, and so on. The statistical being the tests and the parameters that we use. Now for the analysis that we conduct. And the computational part is the code, the software, and the actual implementation of how you did those things. And we are often taught that the empirical and the statistical part, we have a lot of practice now. We writing manuscripts since, I don't know, bachelor's, but the computational is somewhat, it's not very, how would I say, it's not very uniform, people's education in terms of, okay, how do I report my code, and how do I pass it to the user? And this is what we are focusing on today. And by the computational environment, we mean the hardware, right? What kind of machine you used, the operating system, is it a Linux or a Windows machine, the systems components. This is usually more relevant for people working with Linux environments. Windows tends to be more standardized. Everybody has kind of the same. Also the programming language and the version. Depending on the programming language you're using, from version to version, it changed a lot. People using the most recent one would be Julia, that developed from 0 to almost 2.0 in the last 4 years or so. So you could have very different results and a lot of errors depending on the version you choose, and as well packages and the versions of the packages you're using, which in R, which is what I'm focusing on today, I'll base my examples on R. This can be a big thing as well. Many of us must have the experience of loading some scripts that you wrote 3 years ago, and then out of sudden it doesn't run anymore because the version changed and the package, they either corrected something or a new bug appeared. And today we are going to focus on this last 4 items, with more emphasis on the packages and their versions, and then some extension of how to reproduce your programming language and the system components in the operating systems, because as I said, we in ecology, we often struggle more with reproducing the packages, like communicating the packages that we're using and the versions. They tend to be more important than the operating system, for example, but I will touch on it as well. So what should you publish when you want to share your code, right? I think this is the most complicated part. how to take care of the things you need to publish. And this is where I return to the step where I say there is a push for increasing reproducibility of our work. We need to document our work better so that others can read and reuse it and don't need to spend resources and time in trying to make the same thing we did but we failed to communicate. But it doesn't mean it has to be a horrible amount of work that you need to add to your current workload. Sorry, I'm just turning on my clock so I keep track of time. And this is the mindset that will conduct this presentation, just so you know. If something sounds too complicated, I usually will have presented something easier. So if we're talking about, okay, what my computational work, right? One of the first things that you can think of that will make your life easier is having a consistent and understandable, intuitive file structure. And by this, I mean having your work organized in this form of a project where you have your project's name with a root folder. You have probably a notebook or a Jupyter notebook like you've been using here in this summer school. Then you have the results of your research organized in a somewhat clear fashion as data, the figures you produce, the tables. You have your script separately. You have tests if you're at that level, and then you have your text for your manuscript and so on. And even there, this can sound like a lot. And this is the part where, let's say you haven't been working with this, you haven't been thinking about it a lot. I'll present you a couple of options as to how to organize your work. We can start with a very simple one, where you have this is the term they use a compendium. This should contain everything you need to reproduce that work. And some of the things to keep in mind when you're organizing is to have some kind of a convention. So something that you remember how it works and it's always the same, because then when you code and when you have to check for that anything is running smoothly, you kind of know where things are because they are always in the same place. You separate your data from your code. This is kind of basic for some, but for others, it's not necessarily the case. Sometimes people mix it all. But this is already a step. You have a description of your computational environment, which we'll go to last. But again, this comes to that idea, okay, you should be able to share what you used. You have a README file to tell, okay, this is part of work conducted by this person, or it's related to this or that paper. You can have instruction notes of how to use and so on. And very important, like you must have learned in Uwe's class earlier this week, if I'm not mistaken, you should have a license where you specify, okay, this is how you can use this work, whether you can distribute, or people can distribute it or not, or they can modify it and share, whether they should give you credit or not. This is where you explain in the license. So very basic setup, so to say. And the reasoning I put it here is it's when you have the notebooks, as you might be familiar with right now, notebooks allow you to have text and code. So you can use the text part to explain a little bit of what your code is doing. And I find it sometimes better to follow than having comments inside the code chunks. This is a bit of a matter of practice and taste, but it really helps the user to read it afterwards and understand what you did. And by the user, I also mean yourself. I don't know, 3 years from now, when you're done with your PhD, your memory decided to erase that time of your life for whatever reason, and then you want to come back to something useful you did, okay, it would make your life easier to understand and get back on track to use your work. Then we can have a little bit of more complexity whereby you organize, you still have your notebooks. So we keep the same structure, right? You have the description with the metadata of the project, who is involved, what types of dependencies, libraries you use. You have a README describing the general idea behind that research you're doing. You have your license, you have your data, and you have your notebook. But let's say you are in a point where you're doing lots of computational work, so you need specific functions. So I call this one like the functional programming file structure. If it's the case that you're writing your own functions and then you just call them in your notebook, right? So instead of having, I don't know, 50 lines that you call every time you need to do some summarizing of a table, you make it into a function, and then you apply that function in the notebook. And then if people need to check what the function is, they know where it is. It is in a dedicated folder. And it's much easier to read, much more pleasurable. And with R, at least, you can also use the docstring package to create, to facilitate people checking what your functions do. This means, of course, you still need to write documentation. So don't forget to provide some basic writing of the explanation of what the functions are doing inside the function files. Then if you really want to go a step higher, you could decide for an R package structure, which is much more complex, as you can see. So you have a couple more files that dedicated to documentation of your functions. But I would say you have more support as well, because the environment that R creates for creating packages is very well supported by automations of other packages that support you. So you can have, for example, you have your functions that you write the documentation for, but then you have the Roxygen package that will create nice documentation files based off your documentation. And besides this example, you also have lots of checks that the package construction environment of R offers you. And they are all very well explained. The R community is very supportive. So this, if you want to get to that level, you can. And don't mix up the fact that, oh, I'm writing an R package, I should publish it. This might be too much. Not at all. The R package structure is completely independent of CRAN or anywhere you want to publish your package. So you can just share it as a package, not necessarily publish on CRAN and so on. And then you can have, I call it the final boss, because this would be like a very, the most complex structure you can have. But again, you don't need to go here straight away. And even here, it's kind of understandable what things are doing. So you have a make file. This might not be relevant for all of you, but this is a file that specifies some order in which the code is run and what expected outputs should come out of it. This is usually for bigger projects with bigger amounts of scripts and features. Then you have the test.r package. This facilitates the implementation of tests to your functions. So again, depending on how much computational work you're doing, it is useful to always have tests. So every time you run your package again, if you're using the R package, or you run your function, you can check that it's actually doing what it is supposed to be doing. You can have a Docker of your work, and this Docker is it's a tool that basically virtualizes not only, we're thinking more right now of, okay, what packages did I use and so on, but the Docker, it visualizes your whole R environment, so your version, your packages, and also your operating systems. This is usually for very computationally intense work. I'm not going to go into it right now. I'm going to go to something simpler. But this is a form that would basically give the user, okay, this is all I did. This is my little machine. You can just come here and click. You don't need to install anything. You just need to play around with it. And we are going to talk about Binder, though, which is a simpler form, you could say, so where you get to play mostly, you worry mostly about the languages that you're using in the packages. And you have Travis, some of you might have known about it. It's called continuous integration. This is when you use Git. It's also a form of checking your work. So if you're working and you are Git, you are committing your changes, and then when you push them to your repository, the continuous integration will run automatically a check of the tests that you have. So if you implement the tests, you use testdet or any other test form to check. After a while, it takes a while for it to run. You get a green sign in your repository saying, okay, it passed this and this test, or it didn't pass. And this is a nice form for you to keep track of, okay, my project is on track or not. Okay, but again, as I said, this is the most complex form possible. A couple of years ago, I set up this, I call this a kit. It's basically a script that creates a very basic form of a very basic file structure. It's actually pretty similar to this one. So that's not a package. This is just a script that I created that once there is a function in there that once you run, you will create this file structure with your project's name and the project notebook. In that case, I implemented it R Markdown for R in Python and a Julia notebook, a Pluto notebook for the ones using Julia. You can set it all up in this in the function, and it creates a structure. And then once you get used to it, you can play around with, okay, I need to work more with an R package structure, or I want to have a Docker for my work, and then you can grow from it, right? That idea again of, okay, I start small, I implement what I can, and then I go from there. Okay, so now you have the set. You have your file structure locally established, so to say. And it has come the time to, I'll actually, let me paste this this link for you in the chat. Just okay, that you can, if you need to access it in the break or anytime after. Okay. Now that you have your file structure, you need people to locate themselves in it, right? And this I found apparently Jenny Bryan, those that follow R development closer might know her name. She's a developer of R, was a professor at University of British Columbia. And she made this very controversial, not controversial, but like provocative claim that if you have a set working directory line in your as your first line in your R script, she will come to your office and set your computer afire. The same thing if you have a remove all items of your all items in your environment line. She will also set your computer afire. And why is that? So the first one, it happens because you are the only one that has that file. So this is not going to work for anyone. Okay, it's not a lot of work to change it, but it can be better. And this one, the remove list equals SL, this also will remove everything in someone's environment, which they might not realize if they don't pay attention to what they're running. So they might be quite pissed off. And it also doesn't do something really important, which is to set up your loaded packages. It won't deload any old version of a package that you have So it doesn't really do what you think it is doing. And here we have a couple of, so here, this is where I present a couple of alternatives. So the simplest one, as I said, it comes from your file structure. You can define relative paths. So you can have your project name, and you start working on your project directory, right? And then somewhere in the first line, you define this relative path. So you're not giving your whole location in a line, you're just giving the relative ones, because those will be true for whoever whoever gets access to your folder, right? As I said, this is a very simple one. Will work basically in anywhere. But a more elegant one, if you're willing to, there is the here package. That it's an elegant way of basically accessing your files without needing to define those special paths. So here we'll detect what is your top level directory, and then you just need to use it to fill in the rest of the paths with here. So there is no need to define those several lines. You can just say here results data and processed, and you will be directed to that to the file you are trying to access inside that structure. And what is nice is that it works across different operating systems. So if you used it in a Windows machine at first, and then you share it, the files that for those of you who might not be familiar with it, there is some difference in the slash orientations between. Sometimes it's problematic between Windows and Linux, but here takes care of that. So your code will look much more clean, and this is also something that will make it once you publish it, it's much more likely that it will be reused, and will also pass quality checks, because this having this complete paths is something that I usually ask people to change when they are trying to publish their code, and so it is not that much big of a step, and it already puts you forward a couple of steps. Okay, so now you have a file structure. People can locate themselves inside it a little bit better. So this is the very basic, how do I would say, so user friendliness you would like someone to have. Then we start with the more tricky part, which is handling package dependencies. And one thing that is kind of tricky to do, but usually helps, is to use packages that are stable. They're established already. So if there is a package under construction on GitHub and you found about it in some deep, very down on Stack Overflow, or I don't know, ChatGPT told you to download something from GitHub, and you saw that the last commit was 2 years ago, it might be worth checking whether there is a simpler way, or not actually a simpler, but more maybe a more complex way of doing it, but that relies on something more stable. So based on base R or some other established packages. But as I said, this is tricky to figure out, because, for example, packages that are we all use, which is tidyverse, you could say they are reliable, but they are not stable over time, in the sense that there is a lot of functions that get supersetted. So sometimes tidyverse, depending on what you're doing, it might be better to use base R. For example, I wrote an R package, and my life would have been much easier if I had used tidyverse, but I used base R because I didn't want to, in, I don't know, 3 years' time, to have conflicts between the versions of I don't know, dplyr that I used that doesn't have that function anymore. So this is a tricky one. Let's go for the more concrete, how do I say, concrete tips that I can give you. again, a very basic way to reporting your computational environment is to use session info, where you can have information about your. Let me get the spotlight. Yeah. So you can check your R version. You will inform people of the Windows, the operating systems you're using. And also there is some information about the packages loaded at any point. I call this very minimal because, again, people have to manually look up those versions, and there are easier ways of doing this. Not for the R version and not necessarily for the R version in the operating systems. This is still useful to report, but for the packages, there is this R package, very nice R package, renv. It stands for Reproducible Environments in R. And this, it's presented as a future-oriented record of your projects. And I say that because this is the type of package you start using when you are working. So you will start recording the packages and the versions as you're using them and uploading them and and updating them, instead of trying to go back and figure out, oh my God, what did I use 2 years ago? We'll have a solution for that, but let's start with renv. And renv presents us with this idea that's not, it's kind of familiar for people working in computer science, but if you're like me, come from a very biology, ecology-oriented focus, you might not be familiar with this idea of a systems library. What most of us do, we just open R, we need a package, we say, okay, install packages, installs, we just look if there is no error. If there is no error, it's a good day, we start using our packages. So this is what we usually do. We download something for CRAM or GitHub or whatever, it gets into your computer. Most of us don't necessarily know where it is. It is in your system libraries. There are a couple of different, you don't need to worry about it, because what we want to focus on now is what renv presents us, which is this project library, which as soon as you have an R script, you call the init function, you call it as it is, pure, inside your project. What it's going to do is that it's going to create a project library called renv. It's a folder that is going to appear in your, let me get so once you initialize this renv, what it's going to do, it's going to, as I said, it's going to create a folder that will contain your packages that you will be using as you start adding them to your scripts. As you start loading them with library, they will, as you start installing them, they will come here. You also have this renv lock pack file. This will contain the package metadata, and this is like the main file that people will need to reuse your work. And you also get a rprofile file that is basically there to keep renv turned on, because this means that every time you install a new package, there is the possibility of you uploading your list of packages. I'm going to show you how in a second. And you also get a gitignore file that will take care of which of those should be committed to your repository. So this is what happens the first time you use renv. You just run init. It's going to create, okay, I will start recording the packages you will use, and every time you not every time, but I mean it's recommended to do it frequently. When you start installing the packages you need, you take a snapshot, you run the snapshot function, and this is going to record in the renv file the information about the package. Okay, dplyr version through to 3.2.2 or something. And as I said, you do it relatively frequently. And once you're done and you want to share, these are the files you would git to your repo. And whoever gets those files, so this is part of your file structure. They just need to rerun. They just need to restore run the restore function, and that function will detect those files and will download the specific packages and create again your own project library. So everything is kind of pretty tight, right? You gave the person, said, look, this is what you need, just run it again. It will build it in your server or your machine, and then you are good to go. But as I said, this is a future oriented. So this is, I started working, I have a new project I'm working now. I will right away run R-init, and then I'll do snapshots. And there are a couple of other functions, of course, that for you to keep track of how the package inventory is going. But sorry, this is what I meant. Like, so when you want to share, these are the files that you want to share with someone besides your whole file structure, of course. What renv won't do? So you take these snapshots, it's going to say, okay, this is the package that you have. But in the meantime, packages might, as you're working on a project, packages might be updated, especially to do with bugs or new features, and our env won't detect them automatically. You need to run package updates with our env. Our env supports it because it's going to run. You can update that package. You can go in your code. You can test it, and then if you see if something broke in your code after you did the update, you can just revert back to the last snapshot that our env took. So this means you won't lose all your work just because you updated a package. You just reverse your library to the state it was before when the package was working, and then you keep your life going. It won't also report your R version. That, as I said, you should inform people by accessing the session info or R version, the version code, the version function, sorry, that you can run in R. R Markdown is also a bit problematic depending on how specific you get with the formatting of your file. Some things might break because the R Markdown is taken care by the pendoc package, and that's not included once you load it. But the pendoc itself has some implementations that help you work around it. And then they are very well documented in the renv documentation. You can look it up. But as I said, this is usually when you have very specific needs for your R Markdown file. And the operating system, as I said, renv won't reproduce it. It reproduces the R environment. But as I said, you can take care of this with the session info function that will provide those informations, and then people can go on and implement those. Yeah, so you should also include this somewhere. Once you share your code, you should include the output of session info and the renv files. Let's say, however, you finish the summer school and then you are, oh my God, I want to share my work so much, but I have no idea what dependencies, what packages I used last year. And there is also a package for this, and this is called the renv package. And it's going to retrieve dependencies. It's going to retrieve the versions of a file and its dependence, the versions of a package, sorry, and its dependence on a given date. The tricky part is that the package has to be available online so that it can actually retrieve. And how does it work? So you basically give a list of packages that you want to check, and you give the date where more or less you think you used it, and then it's going to report it back to you. Okay, on this date, this was the version, and so on. And here I just showed you, so these 4 packages, some of them are the ones that Cedric used in his presentation, and I also added read-excel because I was hoping that this one would have changed a lot. But as you can see here, we can see that ggplot didn't change much in 4 years. readr got a new version. dplyr went from version 0 point anything to version 1 established, and read-excel actually is the one that changed the most. But you can expect the amount of change that you would see in the functions between versions with this jump, right? So you would be much better off if you want to report work done in 2020. You would be much better off suggesting these versions than anything else. And once you do this, what can you share with people? You can share a list of, oh, there's an error here, sorry. But you can share just that list of packages and versions and tell the person, look, this is what I used. Good luck installing them. You can share an installation script because reng has this export reng function where you basically get this graph. This output here of the resolve function, they call this a graph of dependencies. And you can use the export reng function to create a installation script for R that is going to install all those old versions of those packages. But the authors of reng, they already caution you that this installation script probably won't work because of dependencies that your system, that the libraries will have, that your system should have, that you should address, and reng simply cannot. So the final thing you could use to share is to have create a Docker computational environment. You can use this graph. So there is a workflow of how to produce, again, this Docker file that will that you can use, that you can share with people. And there, as I said, you would have the necessary operating system and the dependencies, everything you need, as long as it's relying on our version, on an R version after 3.1. If it's older than that, then you won't be able to Dockerize it. I won't go into detail into Docker because it would require its own hour of teaching and practicing, but there's a lot of support for doing it in R. Just remember that this Docker is a tool that will allow you to share basically your whole computer to the other person. Whereas here we are more worried about sharing, okay, what is my R computational environment that I will give to the other person. And we come finally to the part where we say, okay, now that I have my file structure that is very nice to read, now that I have some helpers for people to locate in themselves in my file structure, now that I have a list of the R packages and the operating system that I need, that I have, and the library dependencies that I might have, where do I go to publish? Not on GitHub, or at least you don't go to someone and say, oh yes, I've published my code on GitHub, and then you give them the GitHub link. This is not this is let's say the most important message of this talk. The before that was just helping you realize how to set it all up, and but this is the part. Don't just put your work on GitHub, because you won't necessarily have chosen a license, which actually GitHub has facilitated, and you won't have a DOI, which is a permanent identifier for your object. And also we have to remember that GitHub is a private-owned company, so there is no, I mean, if GitHub goes down, other things are probably going down as well, but there is no guarantee as established repositories should have of a long-term archive, minimum 10 years. So these are all reasons why just saying it's on GitHub is not enough. But as I said, GitHub actually facilitates a lot of this. And this is what I want to show you here. So this is an example of a repository that I'm using for this class. And let me just move my, here, yes. And here you can see this release page. This is where you are going to go if you want to publish something. So this is why it's called release, right? You're saying, okay, here is something new for you. You can just release this. This will just mean that, okay, now there is a version 1, version 2 that I want people to check it out. It makes it easier to refer to it. But there is an even better way of doing this, which is using Zenodo. In Zenodo, you can go in, zenodo.org, create your account, and a very useful step is to link your accounts, your GitHub account and your ORCID account. It's a rather straightforward example. You just need to enter, a straightforward process. You just enter your username and your password, and you have all of these connected. And this makes it much easier to publish code, because once you go to this GitHub tab of your Zenodo menu, you have the instructions perfectly laid out. Okay, how do you publish a GitHub repository? And you can simply follow it. So in this case, you just need to toggle a switch on, saying, okay, this is the one I want to publish. So here I'm going to find, I have several repos, but I'm going to toggle this one on. Yeah, so I signaled that I'm going to publish this one. I go to back to my repo, and I create a tag. I'm just going to call it 1.0.0. There is an instruction here about how to choose these numbers. This is very useful reading. Most of us won't go beyond version 1 or version 2 maybe, but it's useful to know depending on how complex your project is. So then you probably should use a title, an informative title. In my case, I'll just call it NFDI, sorry, for bio. Winter School. So this is the version that I'm using with you guys. You can add some description, of course, depending on how much information you want to convey to the user. And then you just publish that release. It's going to create a zip of your software, so to say, of your code. And then when you go back to your repository, you should have the wait, where's you load your where is my here. Yeah, you go on your repository, sorry, will appear in the repositories that you said, okay, I want to publish those. And then on Zenodo itself, you can check your DOI, and then this means you have successfully published your code. This is when you integrate it with GitHub. You don't always have to. You can go straight to Zenodo, upload your files, and then get a DOI the same way. So I find it easier because we're always working on GitHub. This integration makes it things very straightforward to use. So why not? But you can just go to Zenodo and just do a normal upload, get your DOI. As long as it contains all the files we mentioned in this presentation, it will be equally fine. So this is what I mean. If you don't want to use GitHub's integration with Zenodo, you can use the repository of your choice. Maybe there is an institutional repository like we have at iDiv, or you want to put it on Dryad or Figshare. The choice is yours, so to say. And yeah, so you remember your file structure, the list of dependencies, get a DOI, get a license in there, and then you share it. Now people know, okay, this is what I need to make it work, and this is how I can use it, and this is how I reference to this person's work. In the title of this talk, of this session, sort of actually in the program of the summer school, we mentioned binder. But I want to make also a distinction here, the same way that, okay, my code is on GitHub is not enough. Saying that you made a binder for your project is also not enough, because binder and Docker, they are very nice ways of sharing your work, and they can make it very precise, meaning that the person will get what they need to run your project. But it doesn't mean that it's not enough for publication in the sense we want you guys to understand, because again, it doesn't necessarily include a license telling people, okay, this is what you can do with this work. You can send it to other people. You have to tell to let me to cite my work, or you need to ask me permission before you share it with other people. You need to ask me permission before you distribute it. There are different software licenses that you can use, as I imagine you saw with Uwe. And again, it doesn't have a DOI for your work. But it is a nice way of sharing, so we can have a look at it. For binder, as I said, for Docker, this would be too much to cover today, but for binder, binder is basically a tool that will create a Jupyter hub from a GitHub repository. So again, if we go back to my repository, I did it earlier. Sorry. This is my repo now. You just need the address of your repo. Sorry, you copy that address, you go to mybinder.org. And here it's pretty self-explanatory. You just need to give the URL of your repo. It has to be a public one though. And this is why later I will mention a couple of caveats about it. There are some instances where you can have a private one, but depending on your IT infrastructure, it might not be available. So most of us will be dealing with a public version. And you just need to click on launch. I'm not going to click it right now because it takes some time. And it's going to take information about your packages and your R version, and it's going to build that R environment in a Jupyter hub. In my case, I created it before, and the nice thing is that once you create it here, you get this section where they say, okay, this is your binder badge. They give you so you can put it on your README like I did it here. So I just copied this because it's for the markdown file. I added to my README, and when people land on this page, they can just click, and they will be headed to my to a Jupyter installation, Jupyter version, a Jupyter hub, just like the ones we're using now in the winter school. It will be that with my Jupyter notebook running and all the necessary files that I have put in there. While it loads, I can show you I'll show you what you need to set it up actually. Yeah, it's charging already. Yeah. So here you have this is all I had in my repo. This is my base, this is my notebook. And here I just had a very basic example of what to do, because the most important things are having your libraries, the packages you want, and to list the packages you want. There are a couple of things that Binder needs to work, so to say. It needs a file called install_r, where you list the packages you want to use. And it needs a runtime file with the R version and the date, so that it knows, okay, these are the packages that I need to use. This is when I need to download them from, so to say, and this is the R version that I need to make sure that is in this environment. And once you have this, you will see that you can just, the person that gets this binder, this link that you gave them, they can just start running your code, and you have the normal outputs of the notebook. Right, in my file presentation, in my presentation, you'll get it in our Zenodo community later. These are the basic files that you need to have. In case you are working with Linux, it's usually like Linux machines, or there's sometimes your packages, they have some library dependencies. You would need they call it apt text file listing those libraries that Binder will take care of loading into an environment. And sometimes you also need to set up some package beforehand for use in your, if you're using renv, for example, you should call renv in a separate script. It's not only about setting up the computer environment, it's like setting up the computer environment with renv and loading and restoring all those packages dependencies that you listed. This would go in this script here. Yeah, and so this is what, as I said, if you want to share a binder, it's all nice and good. You create these files, you share the link that they have, but as I said, it's not the same as publishing. And one thing that to keep in mind about Binder, sorry, I should make this, is that if you, Binder is going to create a Jupyter Lab based off your GitHub. But at this point, I imagine you learned not to publish your data on GitHub. What are the alternatives? First of all, your data cannot be, if it's your own data and you published in another repository where they gave you a license that allows distribution, then, and it's not big data. I think there is a limit of 10 mega or something. There is some limit to how much you can have in a Binder Git repository that it can actually establish it can actually create a binder for you. So if your data is not so big and you have a license to put it on GitHub, then yes, put it in there in a nice, in a folder called data, and then you call it in your notebook as normal. The alternative is to read it directly from a web server with some some script that can access it. It's not always necessarily possible because of the way that repositories are set up. You might not be able to download it remotely. Or this is something that I would recommend, is that you instruct the user to download your data from wherever repository it is at, and then they can download it in their local machine or in their server, and then load the data to the instance that MindBinder creates. So in our example here, this would be, you see here that I read the data from the data folder, but I don't have any data folder here because I didn't want to add all this data to my GitHub account. But what I can do is this is my instance, right? So I can just create a data folder, and then inside the folder, I can just upload the file that I want to work with. It's going to be in there, and then I can run. I don't need this line here. I can run my line, and it's going to read my file normally. Remember that this is only an instance, so any of those changes that I just did, they won't affect my original GitHub repository, so you can play around as much as you want. And then the rest is going to run smoothly as they wish, as the user wishes, right? Okay, so this is that for MindBinder. Remember, it's a nice way of sharing, but it's not the same as publishing. Then we're coming to almost an end. Another important part about publishing your code is that it's probably going to be published in association with a manuscript. And this is something that I had to do lately, not lately, but a couple of months ago, which was sharing anonymized code for reviewers. And this could be kind of tricky. I could just go inside my code and then look for all the mentions, all the parts that list my name, or I go into the description file, which is the one that contains the metadata. But you can actually do it in a more thorough way with the anonymous GitHub webpage. This is an address where you go in, you connect to your GitHub account, similar to how Zenodo does, and you just choose the terms you want to anonymize. As I said, this is usually the names and emails and affiliations that might be written in some part of your code. And this page is going to create a completely anonymized repository that is not going to affect your original repo. So this means that there is no need for you to create a version of a repository that is totally anonymized, make it public, because even making it public will already take out the anonymous part of it, right? It's connected to your GitHub account. Everybody knows who you are. So this is a much smoother process. The annoying part is, as I said, it won't work with the free version of MindBinder because the MindBinder needs a public repository to work with. If you share it with people, people will know where that's coming from. This is the last thing I wanted to remind you. So just to maybe wrap up, here are a couple of references to the papers that I use that go in detail about these workflows and so on. But the basic idea is have a easy to use, easy to navigate file structure, help people, give a couple of helpers to the users navigating it with here, for example, record your package dependencies with renv or reng, and inform people of your R version and operating systems with session info. And then remember that MindBinder and GitHub are not ways of publishing code. Publishing code is separately. GitHub is a nice way of working and having a nice workflow in developing. It's a very nice tool for that and managing the development, but it's also not where you want to publish it. And MindBinder is a nice way of sharing your R, Python, or Julia work in a way that people won't have to do much work to interact with it. And that's it from my side. I'm open for questions now.